Hey guys, Kenna here. So today we're going to go ahead and do some notes on scientific notation and significant digits. Okay, so let's start with our essential questions for today. Number one, what is scientific notation and how is it useful? Okay. If you guys did IB Chem, for example, you would have already probably gone over this, but I know that some of the math classes do this as well. Number two, what are the similarities and differences between accuracy and precision? They're not the same word, even though many of us use them interchangeably. But in physics, they have very specific meanings. And so we want to make sure that you understand what those are so that you can use them appropriately. And then number three, what are significant figures and how are they calculated? Again, this you probably would not have run into unless you did take IB chemistry. Um, but this is something that if you're going to go into a science field in college, you'll definitely have to do a lot more of. We'll give you an introduction to it here, and we'll kind of leave it at that, and you can go over it more when you get to the next level and start doing more of this. All right, so let's go ahead and get started with a look at scientific notation. So, what is scientific notation? Well, scientific notation is the way that scientists easily handle either very large or very small numbers. To give you an example, if we were to give you this number, 0.00000000056, we can see that that's a pretty small number. When we look at this, we used to have to kind of count how many numbers there were, how many zeros. Okay, we've got 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then the 5, 6. Now, there are 8 zeros here, and using whole numbers is typically easier than using big decimals like this. So, what if we were to go ahead and change this to 5.6? Okay, well, it's not accurate. But it is accurate if we do 5.6 times 10 to the negative ninth. This accounts for the 8 zeros and the 5 that we made from a decimal to a whole number. Okay, 9 place values. Because remember, if you times anything by 10, it's simply moving the decimal. And if you do 10 to a negative number, you're making the number into a small number, less than 1, greater than 0. But if you go ahead and make a positive power to the 10, it's going to be a large number as you're going to move the decimal to the right. Okay, so instead of writing 0.00000000056, we can then write 5.6 times 10 to the negative ninth, and it represents the same thing. Okay. Now, in order to go ahead and do this, we have to have some idea of these powers and how they work. We can think of 5.6 times 10 to the negative ninth as a product of two numbers. 5.6, the digit term, and 10 to the ninth, the exponent term. Okay, so here are some examples of scientific notation. 1 times 10 to the fourth is the same thing as 10,000. 1 times 10 to the third is 1,000. 1 times 10 to the second, 100. 1 times 10 to the first, 10. And 1 times 10 to the zero is 1. Anything to the zero is 1. So you got to kind of keep that in mind. 1/10 or 0.1 is equal to 1 times 10 to the negative 1. 1/100th or 0.01 is 1 times 10 to the negative second, and so on and so forth. So you can see some examples over here on the right. 24327. You always move the decimal so it's right after the first number. We wouldn't want this to be 24 times 10 to the third. No, we want this to be 2.4 times 2.4327 times 10 to the fourth. Okay, so when we go ahead and do this, we can actually go ahead and kind of follow if you want. So if we move the decimal 1, 2, 3, 4 places, that accounts for your 4 here. All right. Likewise here, 7.354 times 10 to the third. It's a positive number, so we go 1, 2, 3, and that's 7354. So if it's a positive number, okay, so if it's a positive number is going to be a shift to the right. Decimal goes to the right. If it's a negative number, though, that's going to shift to the left. And we can see this if we look down here at the bottom, right? 5.3 times 10 to the negative 2. Since it's negative, instead of going to the right, we're going to go 1, 2. That's our decimal. So it's 0.053. There it is right there. Okay. So positive goes to the right, negative goes to the left. And that's in terms of our exponents. Okay. So that's the basics of how we go ahead and do exponents when we go ahead and look at scientific notation. But it makes it in many respects a lot easier for us to be able to go ahead and see when we go ahead and use the numbers. All right, so now when we go ahead and look at this, there are two terms that we use interchangeably in common speech that are not actually the same thing. The first of these is accuracy. Accuracy refers to how close a measured value is to a known value. If you're in a lab and you obtain a weight measurement of 3.2 kilograms for a given substance, but the actual or known weight for that substance is 10 kilograms, your measurement's not very accurate. In this case, your measurement was not close to the known value. But if we had a known weight of 10 kilograms and you got 9.8 kilograms, that's far more accurate than the 3.2 from our first measurement. That's different from precision. Precision refers to how close two or more measurements are to each other. Using the example from the previous slide, if you weigh a given substance 5 times and get 3.2, 3.2, and 3.2 kilograms every single time, then your measurement is very precise. Not necessarily accurate because it was supposed to be 10, but you're getting good precision because the measurement is very repeatable. Okay? So precision is independent of accuracy. You can be very precise but inaccurate, as described in the previous slide. But you can also be accurate and precise, okay? Or accurate and imprecise. How would that work? So let's say if we had a bullseye and we're going to go ahead and fire arrows at it. If we shoot and we don't get very close to the bullseye on any of them, but they're spread all over the target, if we average them out, we may end up with a point that's very close to the target. In that case, it would be accurate, but not precise. Okay? So, if on average your measurement for a given substance is close to a known value, but the measurements are far apart from each other, like I just said, you have accuracy without precision. A good analogy for understanding accuracy and precision is to imagine a basketball player shooting baskets. If the player shoots with accuracy, his aim will always take the ball close to or into the basket. If the player shoots with precision, his aim will always take the ball close to the same location, which may or may not be close to the basket. A good player will be both accurate and precise by shooting the ball the same way each time, and each time making it into the basket. So another example is the example I was giving you. Let's say you're an archer and you're shooting at the target. In this visual, and I think this is a very beneficial picture for us to take a look at, you see different combinations of accuracy and precision. In the top left, you have low accuracy and low precision. They're not going to average out close to the bullseye, but they also aren't very close to each other. In the top right, you have low accuracy but high precision. All of your shots are very close to the same point, but they're not on the bullseye. When you get to the bottom left, high accuracy, not the best precision, better than on the top left, but they're not all in the same spot. But if you average them all out, they're going to end up coming right into the bullseye. And in the bottom right, you have high accuracy and high precision, where both are close together for all your shots and they're on the actual bullseye. Okay. So that's accuracy and precision. We've already gone over scientific notation. The next piece is to take a look at significant digits. Now, if this is your first time, be patient with yourself. I know plenty of college kids who still struggle with significant figures. All right. When we're doing measurements and as we start working on our re-engineering of the whirlybird, I'm hoping that you're making measurements, that you're going through and you're redesigning with a mind of repeatability. But no matter how good a measurement you make, it cannot be perfectly precise. Okay? Let's say we're going to go ahead and measure a wooden stick that's about 2 meters long. If a scientist were to measure that stick with a ruler marked only with meters, then he could only conclude with certainty that the stick was measured at a meter long. Though, of course, he would recognize that his measurement was inexact. If his ruler, however, was marked with decimeters, then he could go ahead and see with certainty that his stick measured 1.1 meters. If he could measure with centimeters, he might be able to see that his stick is actually 1.12 meters. And if he's using a ruler with millimeters, he could actually see 1.121 meters long. So with each gradation, our accuracy is improved in terms of how close we are to the actual measure for the length of that wooden stick. Now, when we start looking at measuring things, some things are going to be super big and some things are going to be super small. And the scale that we use to go ahead and measure is going to matter in terms of how accurate we can measure it. No scientist can use a ruler to great effect for distances smaller than a millimeter. They'd need something like a caliper or some sort of finer tool than simply a ruler. Um, but it also works on really large measurements. Okay. We have to go ahead and find a tool that's going to be time appropriate. We're not going to try and go ahead and measure multiple miles in millimeters. It's just inefficient. Okay. So we have to keep these types of scale issues in mind. We have to also, when we write down a number, realize that we are assuming a certain level of precision. And we don't want to imply more precision than can be justified by the accuracy of our counting or measurement tool. So counting digits is a terribly clumsy way of implying anything about precision or accuracy. And it's more commonly encountered in the classroom than it is in the real world. However, in the research lab or in real world situations, and I think about the times when I was in, uh, working in pharmaceuticals and we were having to submit to the Food and Drug Administration, we have to guard how many digits that we go ahead and put out there because we don't want to put out data that is not as accurate as we say it is. And so any digits that we use minus placeholders are considered accurate. And this implies that you should not round until you complete all of your calculations. Once completed, however, then you want to apply appropriate rounding and uncertainty to your results. The most significant digit is always going to be the first digit of a number, the most left non-zero digit. Okay. Similarly, the least significant digit is the last digit in a number, sometimes, but not always, the rightmost digit. A number is called more significant because it carries more weight. It means we are more confident in that measurement being accurate. In the decimal number system, base tens, like the metric system that we use most of the time in physics, the weight of each digit to the left increases by a multiple of 10. And conversely, the weight of each digit to the right decreases by a multiple of 10. And so when we are doing it, there are some rules we have to keep in mind. And so this is probably the most important thing for you to make sure that you understand. You'll get a worksheet to go ahead and practice this, but these are the rules you need to pay attention to make sure that you know how to do significant figures. And if you struggle, please come see me. I'd be more than happy to kind of go over these for you. All non-zero digits are significant. So if we look at a number like 87.636, that will have 5 sig figs because all of them are non-zeros. 2, any zeros that are between numbers that are non-zeros are considered significant. So in this example, 40.02 has 4 sig figs because those 2 zeros are between the 4 and the 2. Number 3, Any zeros that follow immediately to the right of the decimal place in a number whose absolute value is smaller than 1 are not considered significant. Okay? So in this example, 0.00057, the 000 are simply placeholders and are not considered significant figures. Number 4, trailing zeros that fall to the left of the decimal place in a number with no digits provided that fall to the right of the decimal place are not considered significant unless the decimal point is clearly put in. So if I write 2000 with a decimal, those 3 zeros are significant. But if I write 2000 without the decimal, those 3 zeros are not significant. The 2 will always be significant because it's a non-zero number. All right. Trailing zeros are only recognized as significant figures if the number they are part of has a decimal point. For example, 450 has only 2 sig figs because there's no decimal after the 0, but 450 decimal has 3. We count the 0. However, any zeros that follow the last non-digit to the right of the decimal point are significant. So if we do 0.002400, we have a significant digit on the right that's a 0. Okay, so if we take a look at this number, these numbers are significant. These are not. These are placeholders. These two become significant because they are after the 2-4, after the decimal. Okay, I know it's a little touchy, but you'll get the hang of it. Okay, it's just not always easy when you're first reading it. You got to really kind of practice it to go ahead and get the hang of it. Okay, so now let's look at actually doing some math with this so we can see how adding and subtracting, multiplying, dividing work with sig figs. When adding or subtracting, the answer of calculation should be rounded to the same number of decimal places. This is not counting total digits. This is simply you look where the decimal place is, and the number with the fewest decimal places is the least accurate, and that's the one you trim to. Okay? When we multiply and divide, however, we are counting up how many actual sig figs, not decimal places, and we calculate to the least number of significant figures. When it comes to decimal points, the position of the decimal point has nothing to do with the rounding. Okay? The position of the decimal point is important only in rounding the answers of addition and subtraction problems, not multiplication and division. Okay, so I want to do a couple quick examples here, and then I will let you guys go. All right, so hold on, get out a scratch piece of paper, and let's do some practice problems really quickly. So I think what I'll do is I'll go ahead and use some examples from your homework today so that you guys can actually kind of see how to work through these as we go ahead and do this. I'll skip ahead from scientific notation because I think that's pretty straightforward to giving you some examples of significant figures here. All right. So I'm going to skip to this next place. Let's see, calculating using sig figs. This is the one I wanted to try. Okay. Hopefully you can figure out the others. If not, please come see me. We can go over it. When we go ahead and take a look at this first one is going to be multiplication. And if you have a calculator or want to use the calculator on your phone, I think that's more power to you. Okay, we want to understand the process, not have math be the limitation. Now, before we go ahead and get started, let's take a look at how many significant figures are in each one of these. Okay, so when we go ahead and do this, there are 3 significant figures with this first one. We've got 1, 2, 3. So this has 3 sig figs. We look at this one, 1, 2, 3. This has 4 sig figs. So when we finish doing the math, and you should always do the math first, then we're going to trim down or round to 3 sig figs. So if you do the actual math, we do 1.35 times 2.467. The answer ends up being 3.33045. Okay, so if we go ahead and start, let's go ahead and start by including that here. 3.33045. Well, this is done just doing the math, what you would get from a calculator. This is not significant figures. If you look at the numbers we started with, one has 3, the other has 4. 3 is smaller than 4, so we must limit our answer to 3 significant figures. And so if we're going to go ahead and do that, then we need to go ahead and get rid of some of these significant figures here. So I'm going to go ahead and get rid of 1, 2, so that we're left with just 3 significant figures. So our answer here would be 3.3. Now, this is where I'm really going to start harping on you guys in terms of your units. We have done dimensional analysis, and hopefully you recognize that when doing this, none of the units are going to cancel. And since it's multiplication, not addition, we don't stay with the same unit. And so in this particular example, we're going to end up with a new unit. In this case, we're going to end up with meters squared. Okay? So we count up the least number of sig figs, trim to that answer, and then do our units. The second one is basically the same thing, so I'm going to skip that one right now, and I'm going to go to number 3. Now we should all be able to go ahead and do this as simple addition, probably even in our head for most of us. So if we add 112.01 plus 35.2 plus 6, we end up with what? 153.21. Okay, so 1.53, nope, sorry, that shouldn't be there. 153.21. Okay, and so when we look at that, that is correct by the math, but what we have to realize is that, oh, I erased the wrong part. Okay, let me go try that again. This is, what was it, 153, I think it was, 153. But this one has none to the right of the decimal. This has 1 to the right of the decimal, and this has 2 to the right of the decimal. This has fewer numbers to the right of the decimal. So we can't imply that we can measure that finely when we're going to go ahead and do this adding. So we need to go ahead and eliminate these numbers to the right of the decimal. Now it's easy because they are less than 5, and so these are just going to be dropped off. But if this number was 5, that would cause this number to round up, and it would be 154 instead of 153. Now we still need to include our units, and you're going to hear me say this all the time, units, 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 units. This is going to be 153 milliliters. Okay, so that's your answer. Okay, so I hope this gives you some idea of how to do it. Try going through the worksheet. If you have questions, please, please, please come back and see me. All right, guys, hope you have a great rest of your day. Take care of yourself, stay healthy, stay happy, and we'll talk to you soon. So long.